cryptography is at least 2,500 years old. And for hundreds of years, as cryptography grew stronger, became more advanced, the underlying fundamentals to it stayed the same, right up until electric computers, which showed us the key weakness of mechanical cryptography and also what the key traits of modern cryptography would need to be. So 2,000 years ago, if you wanted to send a secure message, a secret message, you would use a secret key and turn plain text into an encrypted message. And the historic and classic example of this is the Caesar shift cipher. So on the battlefield, Caesar would quickly encrypt this message. And the secret here was how much you were shifting the alphabet by. So in this case, A would become a D, and all of his lieutenants knew what this number was. They had a shared secret key. So this process creates a message that could safely travel in the public domain. So even if this message was intercepted, to most people it would just seem as gibberish. It was only the lieutenants who knew how to reverse the shift by the secret number. And then this morphed over time into a more robust yet still simple idea of using small phrases as your key. So in this case, B would be encrypted as an O, F as in a Y, P as in a G, and so on. And a point here is, people knew this was a known process, what this process was, that the sender was using a secret shift. But it was the size space is what secured this encryption. So for someone to break your encryption, they would have to guess and check all of the potential secrets that you could be using for this alphabet. And this was an enormous number to the point that it was completely impossible to do this. So in the 9th century, cryptography had its first major advancement. So our language is full of patterns. So this is showing the number of times that a letter will appear. And then this chart is showing, 2-letter combinations. The frequencies in our language are actually highly predictable. So in the case of this example message, we see these two M's back to back. We can make a lot of inferences about the plain text version of these two letters. So in this case, we know these are most likely either O's or E's. And with this type of logic, these brute force attacks became much more feasible. But then cryptography was upgraded. So we evolved into multiple alphabets where each input would rotate to a new alphabet. So here input number 1 would go through to this secret alphabet, and then input number 2 would rotate or would go into a second different secret alphabet, and so on. And with using only 4 alphabets in this example, you can see the elimination of patterns because we have 2 S's here and the plain text, but they're represented by 2 different letters, A and Q, in the ciphertext. So the multiple alphabets, they would flatten out or diffuse the patterns and mostly eliminate these logic attacks. This then morphed into the Visa-Nera square, where you had just one small secret phase, and it gave you multiple mini unique alphabets that you could cycle through. And then mechanical cryptography culminated with the Enigma, so the infamous machine that was used by the Germans in World War II. And this is the construct of this process. So shown here to plain text, this is the operator keyboard. This was the plug board settings. You could cross or switch up to 12 letters. And then the rotor settings, you could adjust the rotation settings on 3, 4, or 5 different rotors. In all, it was a very small secret key, just consisting of these settings. But it would allow you to use trillions and trillions of different secret alphabets. But still, these trillions of alphabets were defeated by what was essentially an electric computer by Alan Turing in World War II. And this is a big point. Computers could easily defeat the multiple alphabet construct. So every input in mechanical cryptography, is a plain text letters. They go through an encryption process and it reaches an output. The secret key is applied, and with the Enigma, these are the plugboard settings, and the P is the plugboard setting, R is a rotor setting. The secret key confuses the link in order to hide the input, but the input is still directly linked or paired to its corresponding output. And the process to move forward here is known and repeatable, and it has to be because encryption and decryption must be predictable and repeatable to even work at all. And then in our human language, we cannot avoid patterns in language. Patterns are everywhere. So to view it now, we have this one-to-one link here, and we have inputs that are full of patterns. And the Enigma is our example, but this applies to all the historical mechanical protocols that we just covered. So this pairing here, in this example, we have 5 secret settings, and we're going to turn this into a linear equation where it's our ciphertext output is the result of a single plain text input. So we're going to write this out like it's a math problem. Ciphertext 1, plain text 1, and all the secret variables that we do not know. But we can make now as many equations that are equal to the number of unknown variables that we have. So we know from high school math, if we have equations that are equal in number to the unknown variables, you can solve for the unknown variables. And there's still going to be some guess and check that happens, but electric computers would take a best guess on the plain text, very quickly cycle through the thousands and thousands of most likely plain text options or plain text patterns, and they would just simply unlock one unknown piece at a time. And that is exactly what this machine did every day in the second half of World War II. It figured out the German army secret key. So what the bomb machine showed us is this was the #1 pitfall for cryptography at the dawn of computers. And this problem was actually defined even before World War II and before the Enigma by Claude Shannon, who is considered the father of modern cryptography. He said everything we just covered, that the heart of modern cryptography needs to solve these 2 problems.